Hello, in this video we'll learn how to impose stress constraints in ParetoWin. To begin with, let's load the 3-hole bracket that we studied in the last video. We scroll down to the model, the 3-hole bracket, and load it. Now, instead of applying the restraints and loads as in the last video, now we're going to upload the project file that we saved previously. Once again, we scroll down to the 3-hole bracket. This time it's the project file. And the first thing you'll notice is that the restraints and the forces and the material have been pulled in from the project file. In fact, we can study these restraints and forces through the edit boundary condition feature. Now the edit boundary condition starts at 0, and as you scroll up, the first boundary condition that we applied was the number 1 was the restraint on these two faces, if you recall, and the type was fixed in all the 3 directions. The next one was a force boundary condition type on this face, with the force being equal to 5,000 newtons. And if there were additional loads and restraints, they will show up as you scroll this higher. What we're going to do now is we're going to increase this force. So this feature here can be used both for displaying and for editing. So now we're going to edit this force from 5,000 newtons to 60,000 newtons, and we apply. The force has been registered, and if you'd like to save this force, you have to once again save the project. Instead, what we're going to do now is carry out a stress constraint topology optimization. Since we're going to do a stress constraint, we will increase the mesh quality to get a better prediction of the stresses. We go from coarse, say, to medium, and we'll run a simple FEA. This will take a few seconds to complete, and we'll look at the stresses. As you can see here, the stresses are significantly higher than the previous video. We're still off by a factor of 2 from the yield stress, and so we have some room for topology optimization. In topology optimization, we're going to play around with this. We're going to reduce this to close to 0, which essentially says remove as much material as possible, but with a stress constraint of 850 megapascals, which is your yield stress. So this is different from the last video. Now we're carrying out a stress constrained topology optimization. All other features have been pulled in from the project, and we leave them as it is. And now we'll optimize. The optimization will take a bit longer because you have more elements, and we are trying to achieve a lower volume fraction, and it will be reported here. We'll wait for the topology optimization to complete. The topology optimization is indeed complete, and we've hit a volume fraction of around 0.2, where the stress is indeed approaching the yield stress. And one can open the topology optimization report, and it'll open up a new window. And if you scroll down, you should observe that as the volume fraction is approaching the limit, you'll see that the stress limit has been reached. So the topology optimization stops eventually, and this is what we refer to as stress constrained topology optimization. You can study the stresses on the model. You can go to the final stress, and you can see where the stresses are maximum, and you can make appropriate design changes. This concludes this video on stress constrained topology optimization.